This series analyzes the mechanics of Amazon Route 53, focusing on how it functions as a high-availability edge transit system for global traffic orchestration. At its core, DNS is the globally distributed directory that translates human-readable hostnames into raw IP addresses, allowing a string like google.com to resolve to a specific IPv4 address. To maintain this global scale, resolution tasks are not read left to right. Instead, they are parsed strictly from right to left to allow for the delegation of authority across different network providers. This diagram maps the DNS hierarchical tree. The starting point is the protocol route, denoted by an implicit trailing dot. Moving left, the tree splits into top-level domains, such as .com. Below is the second-level domain, the uniquely registered name, like Amazon.com. Further down are subdomains. Together, these layers form a fully qualified domain name, or FQDN, providing the absolute path to a specific host. This right-to-left hierarchy allows the global network to shard and delegate resolution. Because each layer only needs to know the location of the layer directly below it, the system can resolve any host name without a single server needing to store the entire Internet's directory. Implementing DNS on AWS requires separating the entity that sells you the domain from the infrastructure that actually resolves your traffic. A domain registrar, such as GoDaddy or Amazon Registrar Inc., handles the domain lease ownership and collects annual registration fees. The DNS service is the network infrastructure that hosts the zone files and answers query requests by resolving hostnames on port 53. A standard architectural pattern is to register your domain with a third-party registrar, but use Amazon Route 53 as your authoritative DNS service. To configure this, you create a hosted zone in Route 53 and copy the generated name server, or NS records, into your registrar's management console. This replaces their default servers and delegates all resolution queries to AWS's global network. This handoff is critical for availability, as Route 53 is the only service in the AWS ecosystem that offers a 100% availability SLA. Once authority is delegated, you define how traffic is routed by creating individual resource record sets. Every record contains 5 mandatory elements: a name, a record type, a target value, a routing policy, and a time to live, or TTL. This grid shows the record types supported by Route 53. Standard types include A records for IPv4 mapping, AAA records for IPv6, and CNAME records, which map one hostname to another. Advanced types handle mail routing and security. MX records define mail server locations, while TXT and SPF records store domain verification data. CAA records are used to specify which authorities can issue SSL certificates for the domain. Route 53 also supports DS records for DNSSC, PTR for reverse DNS lookups, SOA for administrative zone data, and SRV records for defining directory service locations. While these records cover traditional network needs, the dynamic nature of cloud resources requires a deviation from standard CNAME behavior. A CNAME record functions by mapping one hostname to another. However, that target must eventually resolve to an A or AAA record to provide an IP address. Standard DNS protocol specifications include a major constraint. You cannot create a CNAME record for the top node of a namespace, which is known as the Zone Apex. As shown in this diagram, you can create a CNAME for a subdomain like www.example.com. But if you attempt to create a CNAME for the root domain, example.com, the request is prohibited by DNS standards. This limitation presents a challenge when routing root domains to AWS resources, like application load balancers, which are identified by dynamic DNS names rather than static IPs. Because load balancers scale and change their underlying IP addresses, hard-coding a static A record is not a viable long-term solution. Standard DNS protocols cannot handle root-level mapping to dynamic hostnames, which necessitated the development of a proprietary engineering solution. AWS created the alias record as an extension to standard DNS specifically to bypass the Zone Apex limitation. Alias records allow you to point root domains at the Zone Apex directly to an AWS resource. Under the hood, Route 53 automatically tracks the IP address changes of the underlying AWS resource. When a query hits the alias record, Route 53 retrieves the current IP of the target, like a load balancer, and returns it directly to the client as an A or AAA record. These records are free of charge and include native health checking to evaluate if the target resource is healthy before routing traffic to it. Note one constraint. An alias record cannot point directly to the default public DNS name assigned to an EC2 instance. For all non-alias records, you must configure the time to live, or TTL. This is the duration in seconds that a local resolver is permitted to cache a resolution before it must query Route 53 again. Choosing a TTL is a balance of cost and agility. A high TTL, such as 24 hours, reduces the number of queries reaching Route 53 and lowers costs. However, if you update the record, clients may continue using stale IP addresses for a full day. A low TTL, such as 60 seconds, ensures that infrastructure changes propagate globally in 1 minute. This provides high agility for failover operations, but it significantly increases query volume and operational charges. For alias records, Route 53 manages the TTL internally to optimize resolution for AWS resources, removing the need for manual configuration. Effective record engineering requires selecting the correct record type to bypass protocol limitations while balancing the economic trade-offs of caching. Records are organized within hosted zones, which serve as the logical containers for a domain's routing configuration. A public hosted zone is accessible via the internet, containing the records that route external traffic to your public endpoints. In contrast, a private hosted zone is isolated within a virtual private cloud, resolving internal queries for private databases unreachable from the internet. This allows internal names like application.internal. Because these zones are invisible to the public, your internal topology is never exposed. AWS charges a flat fee of 50 cents per month for each hosted zone you create, regardless of whether it is public or private. Hosted zones act as architectural perimeters. By selecting a zone type, you define the reach of routing data, strictly limiting where your infrastructure is visible. We analyzed how the DNS hierarchy is parsed and how authority is delegated to Route 53. We addressed the Zone Apex constraint using alias records to target dynamic cloud resources, and we established hosted zones as the primary containers for isolating public and private traffic. These foundational routing mechanics are the prerequisite for building high-availability systems. In Part 2, we will engineer automated DNS failovers using Route 53 health checks.